All right, this is Unit 4, and we are on page 8, talking about circular motion. Remember, circular motion is an object that is moving at a constant speed at a constant radius. So it's going in a circle. It has a constant speed, but it does not have a constant velocity because its direction is constantly changing. And because the direction is constantly changing, we would say that it is constantly accelerating based on this change in direction. So calculate the velocity necessary to orbit the Earth at its surface. So I'm going to draw a quick picture here. So this is what it looks like. If this is the curvature of the Earth and you're standing on a mountain, if you were to do something like shoot a gun, it would start out in a straight line. And let's say you shoot it horizontally. So it would shoot out in a straight line and then it would fall like this. Or if you shot it at a higher velocity horizontally, it would go farther, but it would still hit the ground. But at some point, there is a speed to where it goes into orbit. And so what we're looking at here here's the centripetal force. The direction is inward towards the center of the Earth. And here is the velocity of this object, and it is in a direction tangent to the circle. Some helpful information. So for this one, r is the radius of the Earth. And so r is about 3,960 miles. But we'll just round it for now and say 4,000 miles. So there's a little bit of math involved here, and I'll run us through it. But really what you want to know is how to do this without all the math proof, basically. So what we need to have is something where the centripetal force, this one, is equal to the force of gravity. This is the basis for this question. The centripetal force, the force directed inward, is equal to the force of gravity. And so we know the force of gravity. If we use Newton's second law, the force of gravity is mass times the acceleration of gravity. And we know the Newton's law version of centripetal force, that is mass times the centripetal acceleration. And so in this question, really the mass of this object doesn't matter because you can divide it out of both sides. So the centripetal acceleration equals the acceleration due to gravity. So if you look back at your formulas a few pages back, you'll find a formula for the centripetal acceleration. And it is velocity squared divided by the radius. On this side, we still have the acceleration due to gravity. We have three things, and we know two of them. We're looking for velocity. We know acceleration of gravity. It's 10 meters per second squared. And we know the radius of the Earth. We're using the number 4,000. Velocity squared equals the radius times the acceleration of gravity. And so velocity equals the square root of the radius times the acceleration of gravity. Using this formula, we find velocity equals the square root of Radius of the Earth is 4,000 miles. And we generally use velocity in terms of meters per second. And our acceleration due to gravity is in terms of meters per second. So let's change. So 1,609 meters is 1 mile, and miles will cancel. Times the acceleration of gravity, which is 10 meters per second squared. And so our velocity equals 8,022 meters per second. If you look at your units up here, you have meters times meters, which is meters squared, divided by seconds squared. And all of that's being square rooted, which is how we confirm meters per second. Now this is velocity in meters per second. Let's think about this in terms of miles per hour, because we are generally more familiar with miles per hour. So 8,022 meters per second. We know that 1,609 meters is 1 mile. We know that there are 3,600 seconds in an hour. We come up with the velocity necessary, 17,950 miles per hour. If you were going to throw a baseball horizontally with the intention of getting it to orbit the Earth, you would have to throw this baseball at 17,950 miles per hour. Or if we were going to have a bullet fired out of a gun, if we wanted to get it into orbit by firing it horizontally, it would have to be shot at 17,950 miles per hour. Calculate the velocity of the space shuttle as it orbits 200 miles above the Earth's surface. So here's what we're looking at. Same formula, velocity equals the square root of radius times the acceleration of gravity. G is a little bit different here. 200 miles above the surface. So let's draw, here's the Earth. Here it is. This is 200 miles. Gravity is actually less. Gravity is 8.76 meters per second squared. So we have to use a different value for G. And then the radius of the Earth, we'll consider that to be 4,000 miles. And so the radius overall that we have to use is 4,200. The radius of the Earth plus the distance above the Earth. So let's look at velocity. 4,200 miles. Let's change that to meters. And multiply that by the gravity at that altitude. The velocity here is 7,694 meters per second. So it doesn't take nearly as much to orbit the Earth 200 miles above the surface. In terms of miles per hour, this is 17,215 miles per hour. So something like the space station is still moving at an incredible rate of speed. A note on acceleration of gravity. So if you look at height versus the acceleration of gravity, at 200 miles, we've got 8.76 meters per second squared. 150 miles, this is a little bit closer to the surface. 9.10 meters per second squared. 250 miles, this is a little further away. 8.68 meters per second squared. And 500 miles above the surface, we're talking about 7.74. And when you're talking about from the center of the Earth, this one is 4,500. This one's 4,250. So you have to include the radius of the Earth in your calculation and not just how high above the Earth is it.